Hello sir and welcome to our progress recording video. Our project basically we building a fixed CPU using C. So basically we will input the RISC-V assembly and then we use Ubuntu to run the compiler from RISC-V assembly to binary file for, and then we input that file into our C code so that our fixed CPU can read and then execute. So let's get started. So we've been watching this YouTube channel, which is the Low Byte Production. So basically, he built a RISC-V emulator in TypeScript. But we're going to take the same idea, but we write it since that. So the cool thing about is that he structured his project really cleanly, like with the separate class for each part in CPU. But as we know that since C does not have any classes, we're going to use the struct function to do the same thing. So the project is gonna have a file structure almost the same like this, but in C instead. So let's create a folder. Create. Wait. Oh. So let's open that folder. Okay. So let's create a file first. So the structure is we must have some basic like the basic after a CPU component, like we have the register, we have like RAM, ROM, and the bus unit. So we must have like a system interface, and we have the fetch stage, which the CPU is gonna take the binary code and fetch. So we fetch, and then we have the decode page, like the decode part, and the execute, so that the CPU know where to execute, and then we run our main program in this file. So let's get started. So each of these will map directly to the one that we just showed, which is this channel, but here in TypeScript. So the register 32 is like becoming the register.h and register 32.c, because the h file basically just the header file. So the system interface becomes the system interface and so on. So let's build the first file, which is the register, which is the basic unit for the CPU to execute. So I might rename this to register 32.h. So in his TypeScript, he has the register 32 class. The interesting about it is that it does not just store one value; it stores two, the current value and the next value. So the reason for that is that because in real pipeline CPU, all the stages compute their next value at the same time. So only after everyone is done, do all those update at once. So the two value system let us stimulate that. Value is what the rest of the system sees right now, but the next value is what you're computing into. So then you call the large.next function to flip them over. So let's start to build it. So we defined um, so we include the library here. So let's create a struct. So type in oh it's in like have an integer here. So we return the register, and then we basically we will call the function. def. So we gonna have the function here. So this is gonna be red because we haven't this is the function that we will use in the .c file, but right now we just list out all the function that we have in the .c file, so it might be red right now, but after we create the .c file, it's gonna it's not gonna red anymore. So say next, this one is the next register. So this is the latch of the next instruction, and we have to register the 2 of the pointer here, and it's the reset. So this one is if. So this is the simple struct. So the three spheres, the value is what everybody reads, and the next value is what the current stage is writing into. So the default value is used for the reset, and now let's implement this function in the actual file. So let's create another one. Just 32 .c. So this is where our code will so we include the register file that we have, so it knows which which function to use. So we have this. Just sure. So we have the pointer to the default value is equal to the show value. Show value here. It's gonna be next value of 32. This one is the register that we have. Oh, I miswrite it. Okay. So we have another function here is to set the next value. So we have to register 32 and then a pointer, and then another parameter here. So this function is gonna have the pointer to point to the next value. Is equal to this. So this will return the value. So okay. So this is the next. So we have this. This will return to the next value. So this is the match of the next. So lastly is we have to say gonna have the reset function. So basically the reset is gonna it's like you're gonna set the value into the default. So this is the reset, and it's gonna return into the default value. Also the next. Okay. So now our register is done. It's pretty straightforward. Like every pipeline stage is going to be made up of a bunch of these register 32, and one of each value it needs to carry through. So now let's go to the system interface. So let's create a system interface file. So system interface.h, the header file first. So now we need the memory. So in his TypeScript, he has a separate file for ROM and RAM, and then a system interface class that acts as a bus connecting everything. So ROM is only like it's only read, but the program loads into ROM, and then the RAM is where the data goes. So like when you use the SW to store a value, so the system interface decides which one to talk to based on the address. So ROM lives at, for example, at the 0, or maybe like at the this address maybe and above. So the RAM live at this address, but it's gonna be above, and that's how he has the memory map. So let's code the interface the bus line. So we have the KI here, system. So I might just copy this part because this is the same. Or we might include another one. So include this one. So we create a enum for it. So we set the byte of our system interface, the memory hub word to 2, the memory word to 4, and this is the memory access. So we set the condition by the enum here. So is gonna be so we set the start of it is this address. So the start address of it, and then the end address of it, and then the start address of the RAM. The RAM here, the RAM here, then the end address of it. So this is gonna be self. Okay. So this is the memory map. So let's define a ROM size. So we define it so it's gonna be this, same here but with times 4. So this is the RAM size, we define it. So now let's create the struct. This is the RAM device. RAM size. This is this is the RAM size. Oh, okay. I typed wrong. So this is going to be the same. Yes. So we have another struct for the ROM device. Oh wait, we have this is the RAM, so we have another one for the ROM. this is the ROM. And so we're gonna have I want to have the system interface struct. So same, and this one is gonna be the system. And we have this this from price is gonna have a pointer here, and also the RAM. So the RAM. This is the RAM. So I might spell this one, that's why the function does not recognize, and this one too. Okay, so let's create the unit of it. So it's gonna be loaded. So the ROM is gonna load into the RAM, and it's gonna have the constant value. So it's gonna have the width of it. You access with my spell it, yes. No. Oh yeah, my spell it. Oh my god. That's why the function does not recognize. Have the same, but this one is gonna be RAM stuff. So we have the same unit and everything, and but however the RAM can read and also write. So ROM actually it just can only basically it can only load and read, but as you know RAM we can make it read and also write. So we have another function for it. So so we have another function for it. So this is RAM, and it can write. So it's gonna write here. It's gonna write. So this is the RAM. It's gonna write into a pointer RAM, and then so we don't need this. So actually we need to address of it, and then the value, and the mem. Okay, so it's this thing, and now we have a system for a function for the system interface. So we're gonna have, so the system interface can read, so now the system interface can have the write function. So we create a type of the system interface, and then the pointer. We have the address of the unit, the integer. now we pretty much everything of our header file of our system interface. So this struct the ROM device hold the program. So basically it will hold the program, and then the RAM device will host the runtime data. So the system interface is hold a pointer to both and routes to read and write to the right one. So this is all the function that we will use. So let's create the actual code file. So system can do this, and then we can .c. Okay. So we must include that file in order to use the function. This one. So this is the first function. Let's ROM device is going to be one. So this is the one. So now we have the function to load the ROM. So if the size is bigger than ROM size, zero size is equal to ROM size. So this is the read function. So it's going to be equal to ROM size minus 1, and we have a switch condition of the width here. So let's see, let's in case it's going to have the mem byte. In case that it's half word. So what we do here, so in case set byte, we will return the ROM is the data of that address. So in case it's half word, so we can return the data is that address. But also we can set the condition to be so if we return or we can set it to be so we base on it and then we multiply it. Okay, so this is how it reads. So basically the ROM in the field is the everything with the zero with the zero FF here, 0xFF here. So same as the uninitialized flash memory, the ROM load the copies of the binary files into it. So the ROM read basically it will handle the byte, the half word, and the word reads. So let's continue with the RAM here. So we have a RAM function to initialize it. So we call the class of the RAM device, and then we map set it to the size of the RAM. So this is gonna equal to the address and the RAM size minus 1. So in case the width is same here. So basically this is the same as the ROM but we might add more here. So basically the width is gonna be the same. So switch. In case the ROM, but we instead of ROM we change it into RAM. RAM. Oh, that's ROM. So, RAM again. Again. RAM. Data. Okay, sure. So now the RAM is gonna write. Basically, it's gonna write those. So we copy this one, but this one is gonna write. So we need a enter 2 of the T here. So we have it. And initialize is address the RAM minus 1. So we still have. So this will return the RAM of the data. So equal to the value of it and the address. Let me break it. The address of it. Oh shit. Address it's gonna have the letter. So this part the value is gonna be 8, so it's okay. It's gonna be +1, so we'll be able to call it. So we're gonna have a break here, otherwise it will run the loop. Okay. So the RAM here is the same pattern, but it can write. It has the write function, and the SWS instruction use this. So the address make masking the keep us within the bound. So let's move to another function. It. So Alright, so I already write the system read, the system interface. So basically, system read checks the address and the route. If it starts with the, for example, 0x 1 and 70, it's gonna be wrong. If it start with the 2, like this one, 0x and 2 and 70, it's gonna be RAM. So everything else is just an error. So the system write is the same, but the only RAM because you can write to ROM. So let's go to the fetch function, which is the pipeline of the fetch.